Lukas Biewald. Lukas and I actually overlapped at Stanford for just a little bit. Lukas doing his undergrad and master's. I was doing my PhD at the time. And then Lukas went on not to do a PhD, instead started a company, Crowdflower, now called FigureEight. That company is doing great, but Lukas decided it's time to start the next company, Weights and Biases, which was just founded about a year ago, I think. And whereas Crowdflower is really focused on how you get your data, Weights and Biases focused on how to manage your machine learning processes. So he got both systems covers that you need to build your systems, build your machine learning deployments. Please join me in welcoming Lukas.
Awesome. Thanks so much. I just want to say before we start that I think everyone else in the speaker list is what I consider like a famous, super successful machine learning researcher. And I think I'm more like you, like a deep learning hacker at best. Maybe not even that. But I really, really loved the last sequence of these classes. I gave a lecture and kind of hung around with the students. And I love it because I'm actually super passionate about, I think, what you guys came here for, which is making deep learning actually work in the real world. So it's my favorite thing. And it's super fun to work with all of you folks, because I think what you're trying to do is exactly what I want you all to do. So, just briefly about my career, because I didn't know if I would get an introduction like that. I most recently founded a company called Weights and Biases. I think you're using it in some of your labs, W&B. I'm sorry about the GPUs having trouble spinning up this morning. And I hope that you find this tool useful. We always make it free for students and personal use. And so if you have any questions about it, feel free to send me an email at lucas@W&B, and I'd be happy to answer any of your questions. I was told not to give a hard sales pitch, but it's hard not to do that when you're inviting a founder of a company to give a talk. Another tool that I recommend you use, and I'm totally unbiased, is FigureEight, which is actually the last company that I started. It used to be called Crowdflower, and it basically helped machine learning teams collect training data. And we worked with thousands of machine learning teams, and one of my favorite things about doing that company was that I got front row seats for 10 years watching companies succeed and fail to deploy what used to be called machine learning and now is typically called deep learning. I also want to tell you a little bit about my hacker cred, which is pretty embarrassing, especially coming after that last speaker. But maybe it's inspiring for you all. I really love hacking on little robots in my garage. And one of my popular things was I wrote a little article on how to make a robot use a $100 Raspberry Pi, run TensorFlow, and do incredibly bad self-driving around my little garage and recognize objects. This is like the only part of the video where they weren't like crashing into stuff. But you actually, you can do this. I put my code online and you can use it and improve it. I think this guy actually recognizes the beer bottle and the ukulele. I promise this isn't canned examples. You'll also notice there's a little cut there because it took like 20 seconds to run the little algorithm. But I will say I actually was in your shoes too, because like when I was in grad school, neural nets were super not popular. I think we barely covered them, and so I kind of needed to retrain myself in this stuff. And I think the best way to do it is just fun projects. So I'm like a huge fan of this kind of thing. I think it's important to acknowledge the excitement around deep learning, and it's kind of weird for me having. And I think for a lot of other people having been in the space for so long to see this. But AI is actually working, and it's actually making lots of people money. I remember when I was pitching my company FigureEight years ago, I was told to take AI out of the pitch deck, right? Because it seemed ridiculous. It seemed like science fiction, science project. I downplayed the AI part of it, right? And that's like obviously completely changed, and I think that's a big reason why a lot of you are here. I think you also probably noticed the AI salaries is probably when I talk to groups of CEOs, this is the thing they talk about the most, which is, oh my God, like these deep learning people are charging me so much money, right? But for you, that's fantastic news, mostly, I think. And I think people are making ludicrous predictions. I've been using this slide for a while now. So this is noticed from 2015. And so, I think the sort of like worst culprit is, and I think they've kind of rolled this back, but I think, Watson, for a while was kind of going nuts with extreme claims. And so, I think that I keep thinking there's going to be an inevitable backlash, but we haven't really seen it yet. But the biggest question that people always have for me is like, what can I do today? And there actually is a lot, right? So I think it's good to acknowledge the really useful examples that you interact with every day or that you could do, right? And maybe the best one is that you can generate pranks. So if you go to AIweirdness.com, you can find many other super useful examples like this. I think the sort of big change, I think this similar thing happened in speech, but I think image recognition basically went from, I'd call it kind of not working to basically working. And I can run a little network in my garage that just recognizes things in real time on a pretty low-powered device, right? This just didn't work in the past. And speech is working. So what do people really honestly do with it, right? One thing that brands do with it, and I know this because they use my products to do this, is they want to just recognize their products in social media. Right? I think this is probably maybe the most common machine learning generalized task that I see, which is kind of incredible, right? You never know that necessarily, right? And this isn't in the academic work, but these brands really care, right? They're, as more and more stuff moves away from text, which is easy to search, to images and videos, which is hard to search, brands really actually care where they're showing up and how they're showing up, and it's super important to them, and they hire big teams of folks to deal with it. We see skin cancer classification. This is a funny example just because it's such a crazy example. I can't believe they did this, but this is CocaCola really does this where you can take a picture of your bottle cap and it'll tell you if you want a prize as opposed to typing in the serial code. And they actually put out a paper on how they did this, and it really does work, and maybe it saves you half a second. I don't know. There's face recognition you've probably seen is gone from not really working to working. This is I use actually just a stock vision system. This is my neighbor Chris. And again, this is no original research. This is using off-the-shelf parts. But this actually really... I wanted to set it up, actually. I have one of those fancy Internet of Things locks, that when I think maybe it could open the door if someone didn't seem angry. But you actually you can only lock it. You can't unlock it over the web. So that was the weak link in my. If anyone knows an IoT lock, let me know. There's also a lot of work in sort of satellite imagery, recognizing animals here from drones. TSA is starting to use it in their sensors, right? They had a Kaggle competition where they found that ML systems could do better at recognizing contraband than humans. Another surprising example maybe is finding counterfeit handbags and products from images. This is a super cool company that was called Blue River that was bought by John Deere for I think $300 million last year, and they basically drive this tractor over crops, and instead of spraying pesticides, they can actually just target the individual weeds that they want to kill, and they can actually kill them with fertilizer, which is super cool, right? So it's a great example where adding little smarts means that we can really, really help the environment. I think there's tons of examples like this. It's one of the reasons I'm so excited about so many people like you being interested in actually making this stuff work in the real world. And they actually got this on tractors, and it's running, and it's continued post-acquisition. We actually see robots that check the stocking on shelves, right? Again, you don't always know if you're not in these industries kind of what's important to folks in the industries, but stores actually care a lot about how well they're stocked, and the people that pay for the stocking actually care about knowing that their stuff is placed on stores where they thought it was. And so you actually, one of the first real robots that you'll encounter as you go around is actually these things that go up and down the aisles, just checking that the things are placed where they were told it's placed. Textio actually has a super useful product where it can suggest changes to language to make your resumes convert better, find more employees. There's a whole genre of things now where it listens to machines and detects when the machine's likely to break from the sound that the machine's making. We see a whole bunch of applications of cancer, right? So like individual cancer treatment, personalized medicine is like a huge thing that we can really do now, right? Because machines can actually, or ML can look at huge images under a microscope, whereas like a human doctor might only look at a little bit of your cancer cells. ML is able to kind of look at the complete scan and draw inferences from it. And there's actually an incredible resource. Siobhans OS puts out sort of like an overview of kind of all the companies like doing interesting things in ML, and it's at siobhansos.com. But this is sort of the whole ecosystem of kind of like startups and companies that exist now to kind of serve all the folks that are trying to build ML systems. So, I think like it's really important to talk about kind of what are the issues, right? Because I would say definitely more than half of the companies that I went into with FigureEight, and this is like hundreds of companies, were disappointed by the results of their machine learning programs, and that's a serious problem, right? So you see a lot of companies where, I mean, these days it's like the CEO will be like, "What's our AI strategy?" Right? Which is a little ridiculous, but they really do think like that, and then they try to do something, and when that fails, it's a big problem. So I think that what it all kind of boils down to is that I think when we look at people building machine learning systems, we see like a nerd who's like sitting at a computer kind of doing something, getting the computer to do something, right? So we sort of assume that it's the same as software engineering, but I actually think it's a pretty fundamentally different process, right? And you can actually sort of see it from the code, right? So like the code that we like normally write day to day, we can like step through it, right? We can understand what it does. When we ship a new version of that code, we change things in specific places where we can diff it and see what happens, right? Whereas two files of an ML system trained on the same data does practically the same thing. If you diff those two files, it's going to be completely different, right? And as RAM and GPUs grows and grows, right, these ML files get bigger and bigger, right? So basic stuff just like storage and diffing and continuous integration, like stuff that's like table stakes for good software development, it doesn't really exist in the same high quality way that it does in ML today. So it's like stuff you really have to deal with. As I think deep learning started off as more of a research thing where people just kind of worried about the training. But when you want to get a reliable system into production and use it, you want to know the provenance, right? You want to know like how that thing got trained, what the training data was. I think a lot of these self-driving cars, when they crash, it's like, what does the Highway Safety Administration really get from them, right? If they just got the code on the right, that's like meaningless, right? You can't just like inspect the code and walk through it. You have to know how it was generated and who generated the training data and what that training data looked like. And I also think this is just such a great example from this movie, Space Odyssey. Like I remember loving this movie as a kid. And even when I was a kid, so apparently when this movie came out, there's a scene where an astronaut plays chess against the computer. And the computer kind of taunts the astronaut in like a casual way, right? And they were actually going to take out the part where the computer beat the astronaut at chess, right? Which was actually solved. I mean, like computers beat humans at chess like 20 years ago, right? Computers still can't like casually taunt someone, right? You have like a perfect NLP system, right? And like no one thought that was like the hard thing, right? Which is like incredible, and I think should give us some pause when we make predictions about when we think like different milestones are going to happen, right? I mean the things that we're naturally really good at, it might be because we're actually like really good at them and they're hard to do, right? So it's really hard to predict a priori what's going to be an easy problem and a hard problem for ML. And so they make these projects really hard to manage. I wrote a Medium post about this that I like kind of summarizes if you want to like read all the things I think about this, but I'll give you kind of the gist of it, or what made me start thinking about this is, I ran a Kaggle competition years ago. Do you guys know what Kaggle is? Are you Kaggle fans? Yeah? OK. So Kaggle is this great site. I highly recommend it. You can go in and you can do these like interesting problems. So I put up a problem, and I offered a prize for who could model some e-commerce data the best, e-commerce search data. And I was pretty excited, right? Like the first week, the accuracy went from like 34% to almost 70%, right? So like, people just like jumped right in there, started modeling the data, and it was fantastic. And I looked at this curve and I thought, man, I bet they're gonna, this contest runs for like 2-3 months. I bet they'll get to 95%, 96%, I don't know. And what happened was the accuracy completely flattened out, right? And I was thinking, if I was managing a team doing this, they would have the same curve for sure, right? Like, I'm quite positive that they got state-of-the-art performance on this data set, right? But, and they actually worked super hard to go from like 63% to 65%. But if I was managing a curve that looked like this, I would be so frustrated, right? Because, it's like 60% versus like 65%. It's like you basically have an unusable system at 60%, still an unusable system at 65% accuracy, right? The error is just too high. And so I think that people look at the first part of this curve, and you look at like the first week, and you just can't really draw conclusions, right? It might be that next week you get a perfect system, and it might be that you will never get a perfect system, right? It's really, really hard to make these predictions, and so people get really frustrated. If you look at this contest, though, because it's on Kaggle, actually these people didn't get frustrated. These people found the competition super fun, right? So like as it got closer and closer to the end of this contest, they started like submitting more and more things. We had over 1,000 teams that participated in this. So I'll also say, if you're trying to see what the state of the art might be on a set of data, Kaggle is a really efficient way to find that out. And in fact, looking at past Kaggle competitions on a data set like what you're trying to solve is one of the best ways to get a sense for how hard your problem is. Do you guys remember the Netflix prize? This is like an awesome thing. And basically, the same thing happened with the $1 million prize and like lots of famous researchers, many years ago. And again, like you see these curves, like Google put out, sort of the miles per disengage with their self-driving car, and you kind of look at a curve like this. This is like back in 2015. And you think, well, okay, if I just sort of like plot, if I like kind of fit this in my mind, I'm thinking like self-driving cars are coming really soon, but you just don't know. Okay, next problem. Machine learning can be super unpredictable, right? And so you see this with like, image classification like works super well on ImageNet, right? It's really fantastic. It recognizes these categories in ImageNet better than a human, definitely better than I can recognize these images, right? But that's as long as the images that you have look just like ImageNet, right? So I was really surprised when I was training my robot. And I trained a little model on ImageNet, and it was working pretty well on ImageNet. And then I put it on the robot, and it was actually kind of messing things up. And I was asking my friend about it, and apparently there's like a known problem with when robots are looking at something, right? Which is that they don't frame it in the same way that humans do. Right, so ImageNet is images of stuff on the web, right? So people kind of tend to put the thing in the center, for example, right? And like, when the camera's not being controlled by a human, you get, this like weird variation where like I wouldn't even notice maybe the difference in these images. State-of-the-art ML is like not generalizing very well, right? It would take me forever to figure out that problem. And you see these hilarious errors like the puppy versus bagel. You guys seen this? I was like, super excited about Alphago. I love playing Go myself, and it was really interesting to watch when Alphago. When I was really surprised, and it really got me excited about the power of deep learning. But unlike Deep Blue, right, when it beat Kasparov, it really didn't like make obvious mistakes, right, because it was more just like a searching system. Alphago is really a deep learning vision system, right? And so it actually made like blunders, right? Which is really interesting and really feel like different. So it won 3 out of 4 games, but in the game that it lost against the expert player, it made a move that I, as sort of like a strong amateur, would have considered a mistake, and it turned out actually it just was a mistake, right? So totally different than the feeling of Deep Blue. And of course now it's like they've trained it more and more, and it's gotten so good that it doesn't do stuff like this. But I think with a lot of applications, we're in this period where deep learning, it's like amazing, 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 and like, oh my God, right? It's like, it's bad. And you see this with like all these Tesla crashes. And there's just one this week, I think, right, where it's like, a truck is like perpendicular across the road, right? And it's like, you don't have that in your training data. You may just like miss that case with the vision system. So there's really like, in self-driving cars, like life or death consequences. And like, it's like, as people start to use stats for this stuff, like, criminal risk scores, right? People using ML systems. And so it really matters, right? Like how the kinds of mistakes that these systems might be making, or the biases they have. And I just point this out. This is like just a little research thing I think is kind of cool, where they're looking at, okay, how might we figure out what the system's doing? And here they're looking at this thing which is like labeled as a dog and a guitar, like an acoustic guitar and an electric guitar, which is actually wrong. And you can kind of pull out, you can cover different pixels and see what makes it change its mind, and realize that it's sort of this piece that's making it think it's electric guitar, right? Which is actually, it's an acoustic guitar. But that's sort of consistent with electric guitar. Kind of interesting, right? That like, a hand doing this makes the system think that it's more likely to be a electric guitar, which kind of makes sense, right? Like it'd be rare to see a human hand pointed up. You may only see it in your training set when you see a guitar. So I think there are really interesting ways to inspect these systems, right? Often by just kind of like running them in isolation and looking at what they do. And I think that's like something that kind of everybody working in deep learning, they kind of know to do stuff like this, to test things before they deploy it. But I don't feel like this is super systematized, which is why coming to classes like this where you kind of get best practices and can share ideas, I think is really important right now for building safe deep learning systems. You may know this, you may know more about this than I do, but I just want to make sure everybody knows, because it really is an issue. Vulnerable to hacking, right? So adversarial systems, you can really use the fact, if you have the model, to find things that will trick good systems, right? So you take a thing that's an image that's like Panda, you add a tiny bit of noise, right? And the noise is discovered using the same techniques that trained your model, right? You add a little bit of noise and it thinks it's a gibbon. You might say, well, like, so what? Like this, this is like a sort of de minimis number of examples, but when those examples are possible to find, you can really use them to mess the systems. Like here, these glasses make the face system think that this person is actually this person, right? This is a good face recognition system. And that's kind of like funny, right? But then it's like, obviously, self-driving cars make this like really real, right? Where you add a little bit to a stop sign, you make it think that it's a right turn sign. That's really dangerous, right? And it's something to know and something to deal with. And then the biggest thing that kind of everybody knows, and then everyone's still disappointed when it's the case, is that machine learning requires training data, right? So this is like the biggest disappointment, right? Machine learning systems are amazing. Vision, for example. I think vision, almost anything where you can blink and look at something and make a decision, it's pretty well can be done by deep learning. And you talk to like the OpenAI guys, and they're just like, oh, like image recognition is solved, right? It's like, OK, it's solved in the case where you have an infinite supply of training data, and the thing that you're going to deploy into, those images look exactly like your training data, right? Which is almost never really the case, right? Peter Norvig wrote this kind of seminal paper years ago at the kind of early days of machine learning, where he pointed out that, look, the examples where machine learning is working, it's not examples that are like easy or hard. It's just cases where we have tons of training data. Right, so like one of the first big successes was machine translation. Right, when Google Translate came out, it was amazing. It was better than systems that people spent tons of time on. And the reason it was amazing is just they crawled the web, and as a byproduct, got all this parallel corpora of things written in one language and in another language. Right, and so what he kind of realized here, which has just been totally a consistent result, is basically the places where machine learning works is where you happen to have lots and lots of relevant training data. And like, this is why I started my last company, right? I was like literally like looking at stuff, and this is like the examples. There's no neural net because it's like predates it, right? But I was like basically looking at like, okay, try naive Bayes on this classification task, maximum entropy, SVMs. Okay, the fancy SVMs are a little bit better than the other systems, right? But again, it's like you're going from like 19% error rate to like 17% error rate. And you do fancier features, you get maybe a little bit more improvement, but then you just like add data and you get way more improvement, right? And so all these companies, they like focus on like tweaking these algorithms, and what they really should be doing is probably like not hiring so many deep learning researchers, hiring like annotators. And I just think this paper on the right is kind of funny in that it's got like, there's like a fancy method and like a simple method, and here like down is like higher accuracy. And they just happen to plot it over different amounts of data. And the point that they're trying to make in this paper is basically that this fancy method, this green line, is better than this red line. But it's kind of funny because it's like you could reproduce this paper by just like getting more training data, right? You completely do the dumb, simple algorithm with twice as much training data, and it would be fine. In a lot of cases, if you can do that, that's really what you should be doing. And then there's the thing that nobody writes papers about because it's I guess it's not interesting, but it's like everyone who works in this space like knows, right? Cleaning your data is a massive effect. right? Because it's the mislabeled results that end up influencing your algorithm the most, right? Because they have the highest residual, right? So if you just clean up those last couple weird outliers in your data, sometimes it's not even mislabels, it's just something different than you expected, right? In kind of real world data, there's going to be just weird examples. And like getting those out or getting those labeled properly is almost always the best thing you can do. And I think it's kind of funny because everyone used to joke about how data scientists say like cleaning their data is what they spend most of their time on. And I always say this is like actually really rational, right? This is actually the best thing you could do is go through and clean your data. And you see this at bigger and bigger scales. I think this is interesting because this paper is like 10, 15 years ago at sort of as many orders of magnitude as people dealt with at that time. And you basically just see algorithms getting better and better as you have more and more training data. And then Andrew Ng has this great talk where he basically points out, like, or his perspective is that deep learning is just a system that kind of keeps working as you add more and more data. And then Andrej Karpati has this great chart. I just like love this chart, right? So I think he spoke at the last full stack deep learning, but since he's not here, I'm going to steal his slide because I love it so much, right? So this is in his PhD, right? Models and algorithms, all his time on this much time on training data, right? And then now he's at Tesla running their self-driving program, and you can see that his focus has changed to data. And so should your, I mean, you should be on the right if you're trying to do, this is the difference between like real world full stack deep learning and sort of like academic deep learning right here, I think. Best summary. And then, okay, this is like a side point. You probably felt it today, right? But this is like, I did a lot of engineering. I thought I had seen my last compiler error, my last like linker problem, like 9, 10 years ago. Like never worried about it, right? Until I started building these deep learning systems, right? And it's like when you like rip out the CPU, replace it with the GPU, right? And then you start using these like proprietary systems and compilers. It's just a huge pain in the ass, and you need to have a friend that understands systems programming. And if you're one of those people who understands this stuff and you're in this class today, I'll just say especially you guys are like the most important people, and my companies are all hiring, and I would love to talk to you. Okay, so why do we do it, right? I think I think one big thing is that you can look at so much more data, right? And so like the cases where you win are cases where, or like where you really beat human performance is cases where you can just look at more stuff than a human would be willing to look at, right? And so this unreasonable effectiveness of data, they revisited it, Google did in 2017, and they basically looked at, continued to look at, okay, like what happens when you have billions of examples? And it's like, well, you know what? The algorithms just like keep getting better and better and better, right? So now we have cases where we have billions of examples of data, and we can still use our algorithms to pull out more information from the systems and build better stuff. There's actually like a really interesting, I'd say like thought-provoking table that I found that kind of argued that breakthroughs in AI seem to come like just after the training set is first made available and like kind of long after the proposed algorithm is available. So this is sort of like real-world breakthroughs, right, when the data set came. I think like one big one, right, is like sort of the object classification we keep talking about, which is probably one of the reasons people are so excited about deep learning. It happened like not long after ImageNet was made, right? But long after convolutional neural networks were a thing. So don't entirely agree with like everything in this table. It's a little bit hand wavy, but I think there's a real truth here. And ImageNet is available as a free data set. There's so many data sets coming online now. I've really been a proponent of this for a long time. I think you worry if all the data is sort of siloed in companies that it creates a really unfair playing field. But luckily, there's a lot of pressure on folks like Google to release data sets. And my company, FigureEight, that we curate and release lots of data sets and make them freely available with really friendly licenses. So anyway, I think if you're looking for a machine learning project to play with, what I always advise people is find an interesting data set. Like it's the best way to kind of have a successful project is start with the data set that you really, really care about. Here's another point that I think people forget, although the last speaker was talking about a little bit, which is that you can really, if you combine humans and computers, you can do way better things, right? And advanced chess is sort of the classic example of like, for a long time after computers beat humans at chess, a human operating a computer was still better than a computer at chess. That actually changed with Google's AlphaZero chess program. So this is no longer true. But I think in a lot of applications, we're still in this world where the human operating computer is actually the best system. And the simple design pattern that I think is in so many actual deployed systems is where you take an AI classifier, you actually use its confidence value. You always get some kind of confidence value from these things. And it's surprising. It's often reliable. Where it's confident, you use its output. Where it's not confident, you get a human do the annotation. And the great thing is, as a byproduct of this, right, you're actually generating the perfect labels that are going to best make your AI classifier better. So just by virtue of running the system, which is now reliable, right, because there's a human dealing with the unconfident results, you actually have a loop that's making your system better and better. And that's why this is such a powerful design pattern for making ML work. And I think the coolest example of this is the Postal Service, which you don't always think of as super tech forward. But in 1982, they deployed an OCR system that only worked on 20% of their letters they were processing. And now it actually still only works on 99.5% of letters. So there's still like 0.5% of the mail is being checked by a human in the loop. I'm pretty confident my grandmother's letters are one of those letters that get checked based on her handwriting. But if they had waited until OCR was better than humans on average letters, right, they would have waited at least 35 years to deploy the system. Right? So when they first deployed it, they got savings because they used it in the cases where it was confident. And there's lots of good strategies, but they're kind of the strategies to do this to generate good training data is kind of exactly what you would think if you were teaching a human. And this Coca-Cola example, because they published how they did it, and this is a real-world deployed thing, they actually used a human-in-the-loop system. So they had a little interface for if you think that some of these letters or numbers are wrong, you can fill them in. It sort of highlights, OK, I think these might be wrong. And then look at this. It's the same pattern, right, where the neural network makes a guess, and then it sends the corrected code if the human updates it. So good design pattern. And then just to give you a real case study, right? So this is support ticket classification, right? So this is a company that has lots and lots of support tickets. Some of them might be about drunk driving, and if it is about drunk driving, they really want to know about it, right? So they have an ML system trying to classify drunk driving. And at first, their tolerance for error was so low that only 40% of the output was confident enough that they were willing to use it. Right? So you might look at that. I think a researcher might look at that and think, 40%, that's a real failure of the system, especially on a pretty easy task. This customer looked at it and they were like, wow, this is 40% savings immediately when I deploy this, right, with the same level of accuracy. And the great thing is it only gets better and better as it runs more and more. OK, so what's coming? I think one thing is better tools and platforms, right? So like I was saying, I think there's this software design pattern, and there's some amazing companies that you can use to handle each of these steps in sort of a software process. I hope that my company, Weights and Biases, does a lot of the deep learning workflow. But there's actually lots of other stuff out there, right? So as you know, Google and Amazon and others put out these amazing frameworks that I think are all very good. There's a whole bunch of infrastructure companies like FloydHub and SageMaker. And then what I want to build, what I love building, is these sort of dev tools that solve simple point problems. If you have any SageMaker, I think this is, I would say, of all the tools out there, this is the tool that I come across the most. There's nobody really publishes stats on this, but I work with hundreds of teams, and so I think I have in my head a pretty good Nielsen rating of ML tools, and I think SageMaker might be the most popular because it's actually really good. It's pretty basic, but it really does good stuff. And then Google's cloud machine learning engine is ambitious, getting better all the time. Qualcomm has a cool thing for deploying things onto phones. There's tons of. We built an autonomous flying, face recognizing, speech controlled drone in our garage.
Hello, Chris. I found you.
Oh my gosh! I love it.
Nice. Sorry. I have a whole YouTube channel that you can, if you want to see stupid videos of really bad research. I think unlike the famous researchers, you can email me and I'll help you copy my work if you want. I think medical applications, sorry, totally different, are incredibly cool. I'm really excited about this stuff. We're suddenly seeing lots of this stuff. I think one of the coolest ones, just because we can relate to this, is a friend of ours is working on ML hearing aid that can like tune out all the people that are not talking to you and only amplify the person who's actually talking to you, so tune out all the background, which I think is something that anyone would want, not just people that are hard of hearing. I think another thing that's coming is new solutions to training data. I mean, there's just so much effort going into this right now because it's such a big issue, right? So I think this is a hilarious data set, but kind of awesome, the Freiburg grocery data set, right? So it's like, it's lots more than ImageNet. It's just like pictures of like food. But it's a great test set of like, what you actually, this is like what you really deal with, right? Probably in your job, right? And one thing that happens is that fine tuning, where you train a model and then you kind of on a bigger data set and you retrain on your data set, it like works extraordinarily well, right? It's like this is not a subtle thing, right? They get 77% accuracy with fine tuning, 47% accuracy without fine tuning. So this is like something that you should really use, right? If you have a smaller data set. And in my opinion, one of the coolest papers ever, right, is taking ImageNet and then fine-tuning it on skin cancer images and getting really good performance. It's just so amazing, right? Like, who would think that ImageNet would have something to say about cancer images? Super cool. Multitask learning, where you try to do multiple things at once, I think, and one-shot learning, where there's different techniques to try to figure out how to deal with something that you've never seen before. Josh actually works on synthetic data, and OpenAI has a whole bunch of results. But I think this is like science fiction, right? Where you take video game data and use it to train like self-driving cars is just like kind of incredible that that works at all. And we're starting to see it like really become part of people's process, right? To make sort of synthetic images that are like realistic enough or connect enough to real world data so that you can use it as training data for something that runs in the real world. It feels like science fiction to me, but OpenAI actually has an excellent blog post about this. And so I'll just leave you with, I think this stuff is like really, really important. And I think people are, we're starting to see like ML in more and more stuff. I think that there's some stupid examples like this oven, this ML powered that I actually have in my office, right, where it supposedly microwaves your food better automatically, but I'm like a little dubious. Oh man, I'm being videotaped. Sorry, guys. Maybe it's getting better. There's also this self-driving suitcase that follows you around the airport, which like I kind of want, but apparently you can't like then bring it on the plane, which is like crazy. And then the world's first AI trash can, which I actually have ordered on Kickstarter, but I have not gotten it yet. So I'm worried that this is vaporware. Maybe you can help them. What's that? Yeah, so I don't know. If anyone knows these guys, I want my money back or my AI powered trash can. Okay. I do think, though, I think almost everyone, at least from the last class, and I assume this class, is actually like coming from a company working on something really interesting, really important, right? I think like you go back and you solve the problems that you have. It's like could not be a more important thing. So I actually want to leave you with sort of my three opinions on how to successfully ship deep learning projects. One, pay attention to training data. Get something working end to end right away, and then prove it one step at a time. Get a simple thing working. And then finally, deal with the inevitable cases where your algorithm fails. That's my advice to you. I really mean it. If you want to email me at Lukas@WNB and tell me what you're working on, if you want advice on kind of like getting into the field and career information, or if you have questions about using any of these tools, I'd love to talk to you. Thank you. Oh, yeah. Do you have questions, or do you want to get out of here? Yeah.
So for cleaning up data, is this just a matter of things that fall in outlier distributions or things that you have the lowest confidence on, just visually going back and checking them and having some sort of pipeline for that? Would that be the best thing you recommend?
Yeah, I mean, I think this is something like Josh actually I think talks about this, but I think like one thing that like you really should do in any case, right? And like I think there's like sort of just like a kind of known best practice. Like run in your training data your model and look at the things that your model is still not classifying right, like the highest residuals on your training data. It's always something weird, right? It's like either like a mislabel or it's something that's just kind of like unexpected. Like you think about like, I mean, any example, there's weird stuff, right? Like picture you're trying to recognize faces, right? Well, what if the face is in a mirror, right? What if it's like a drawing of a face, right? There's just so many cases where you might have a label that's different than you expect. And in big data sets, you always find them, and they have just an outsized effect on the quality of your results, yeah.
Any hands-on findings?
Well, like I was saying, I think one thing is to look at the stuff where your model's struggling to classify it, like even though it was trained on it. There's other techniques actually. I mean, like another thing you do is like if you train multiple models, you can look where all your models are struggling to classify something. That's almost always something you want to pay attention to, because like think about like a best fit line, right? Like the best fit line is going to be far more influenced by an outlier, right? A single outlier will move a best fit line like a lot, right? And it's sort of the same thing with deep learning models, just in like way more dimensions, where like something that's like different that it can't fit is going to really shift your model that you're shipping. So, yeah.
How is it possible to label a time series data? Do you have a solution for it?
To label a time series data?
Yes.
Well, I think it's like anything else, right? I mean, labeling is like a complicated thing. It depends on what it is, right? Sometimes impossible, right? Like, if you want to predict like stock prices into the future, well, you can't get those labels, right? But you can get a lot of historical labels. I mean, do you have something in mind that you're worried about labeling, or?
Like signal you can get from an antenna or something like that, and you can find an anomaly or
Oh, I see. Yeah.
missing in the connections between like two servers.
Yeah. I mean, I think it's hard to say something like sort of general about labeling. I mean, it's just that every case is complicated, right? You often have to get experts to like do the labeling, or I'm not sure. Yeah.
So you were saying that deep learning products. So what's the most lightweight infra combination? Data warehouse, all those things we talked about this afternoon. So what's the most lightweight for like just one people, two people could handle everything?
Most lightweight infrastructure?
Yeah, from data injection to management to build models and tune parameters and like everything and deploy. So, right.
Most lightweight thing is probably like CSV files fed into like Keras.
The easiest.
Well, look, I think like an underrated framework is scikit-learn, which is super convenient and helpful, but doesn't handle neural nets very well. So often it's kind of nice to start with scikit-learn, and it's pretty helpful framework. I think Keras is by far the simplest framework to kind of deal with, and I think it's like people think, oh, there's like a toy framework or I can't deploy it. I see tons of people that their deployment is literally just calling like model.predict in Keras, right? That's not actually that bad, and often the actual model running isn't really your bottleneck. Often it's like the pre-processing of your data that's the more painful part. So for many applications, that's just a fine way to do it.
Yeah, but in the machine learning project, the real modeling part is very small, let's say 10%, and then the rest 90%.
Yep.
But on the other hand, we would say the need is in the 10%. So my question really is how to make the rest 90% as small, as easy, as lightweight.
Yeah, totally. It totally depends on your application. I mean, my recommendation is like start with like the simplest possible thing and add complexity as you need it, right? So the simplest thing, it might be just like some Python scripts, right? And I think like you should slowly add the complexity when there's like a reason to add that complexity.
Okay.
Yeah.
Great.
Awesome.
Thank you, Lukas.
Thanks, guys.